안녕하세요. 안녕하세요. 자, 잘 들리시죠? 제가 이따가 또 얘기하겠지만, 엑스트라 홈워크로 낸 거 있잖아요. 다음 주 금요일까지 하는 거. 거기에 그 오타가 있어가지고, 오타라기보다는 오류가 있어가지고, 제가 그 첨부 파일을 새로 올렸어요. 그래서 엑스트라 홈워크 하실 분은 그 첨부 파일 다시 다운받아서 제가 고친 부분은 빨간색으로 표시했거든요. 정확히 어디냐면, 제가 보여드릴게요. 이게 나오네. 잠깐만. 아니, 이게 아니고. 네, 이 부분에서 요 밑에 여기 그 매트랩 코드 있죠? 여기 방향장 그릴 때 매트랩 코드가 잘못됐고 그 제가 그거 해석한 부분이 또 잘못됐어요. 그래서 요 부분 빨간색 된 부분 요거 고쳤어요. 그래서 요거 다시 보시고 하시면 됩니다. 그리고 그 전에 학교에서 뭐 조사한 게 있었던 것 같은데 그 우수 온라인 강의 사례 거기에 이제 선택을 많이 해주셔가지고 오늘 강의하는 거 짧게 찍어서 인터뷰 영상이랑 함께 달라고 하시더라고요. 그래서 오늘 강의 중간중간에 제가 잠깐 카메라 옮기러 조금 돌아다닐 텐데 좀 양해해 주시고 인터뷰 영상 때 여러분들 뭐 준비된 인터뷰 질문들이 있는데 혹시 여러분들 궁금한 거 있으면은 인터뷰 영상 통해서라도 제가 말씀해 드릴게요. 그래서 뭐 궁금한 거 있으면은 지금이나 조금 있다가 다시 한번 얘기해 드릴 테니까 알려주세요. 근데 요즘에는 잘 안 들어오네. 애들이 친구들이 좀 그 실시간으로 보는 사람이 별로 없네요. 지금 17명이고 LMS 들어온 사람은 반밖에 안 되는데 8명밖에 들어왔거든요. 중간고사에 매트랩 나와요. 매트랩을 해야만 할 수 있는 문제가 나올 겁니다. 자, 10시 넘었으니까 한번 시작해 볼까요? 오케이. Okay, let's start. So last time we talked about linear approximation of system of differential equations, and one of the example was Lotka-Volterra predator-prey model. And by linear approximation, we found that the nature of stable solutions, there are two stable solutions. One is 0, 0, where there are no prey or no predators, so there's nothing happens. And another stable point is L over K, A over B, where L, K, A, B are proportional constants in the model. And at that point, there are perfect equilibrium, and by linear approximation, we know that the stable point at this point is the central node. So there is always circling of the population of predator and prey. Okay, so no species dies off. Okay, and we are going to see a few more examples of system of differential equations. So one of the example is van der Pol equation, and this equation is basically second order differential equation, not a system of differential equation. But interesting part is that there is the first order term whose coefficient is negative, and also it depends on the sign of this coefficient depends on the size of y. So we have 1 minus y squared here. So if y is less than, the absolute value of y is less than 1, then the coefficient is negative. And if the absolute value of y is bigger than 1, it's positive. So what that means is that you can consider this. So you can consider this coefficient as something similar to damping force. Okay. So in a spring motion or circuit model or other physical model, the damping force is always applied to the negative direction to the moving direction, right? Opposite direction to the moving direction. But in this case, in this van der Pol equation, the sign changes depending on the size of y. So if you have a damping force applying as a negative, then it means that damping force is not actually damping the movement, it actually accelerates the movement. And if the damping force is positive, then it works as if it's a damping in the spring or other circuit models. So we were going to draw this equation, a numerical solution of this equation, shortly by MATLAB. And let's review some of the aspects of this equation. So basically, you can solve this second order differential equation by system of linear differential equation. One is if you set this y1 equals to y and y2 equals y prime, then y1 prime, which is y prime, is equals to y2, and y2 prime, which is equals to y double prime, is equals to mu 1 minus and so on. Okay, so I'm not going to write it all down here. So these are the system of first order differential equations, and you can rewrite your y double prime, which is y2 prime, in terms of y1 and y, because now this y2 prime is dy2 dt, and this can be written as this dy1 dt multiply on the numerator and denominator. And if you're looking at this part, this is nothing but the derivative of dy2 over dy1. And the last part, this factor is y2. So you might wonder, what's the meaning of derivative of y2 in terms of y1? because y2 and y1 comes from the same function y, right? In this case, we are considering y1 and y2 as a separate variable. So although y2 is a derivative of y1, so derivative means that it measures the velocity of the movement, right? And the original y measures the movement of the object. And in a general situation, okay, in a general plane, your direction of movement or the velocity of the movement does not depend on the location of your point. So the location, the variable, which is y1, and velocity variable, which is y2, are linearly independent. There are two different variables to model the situation. So that's why we're talking about dy2, dy1 here, okay? And if you rewrite your van der Pol equation again, this y double prime replaced by these ones, then your equation looks like this. So basically, I divide y2 by left and right side, so we get dy2 over dy1 equals to these. So when I take this dy2 over dy1 equals to k, that means if I make a plane whose horizontal line is y1 and vertical line is y2, so although, again, this y1 and y2 comes from the same function y, but I'm taking as a separate variables, then the dy2 over dy1 measures the slope of the curve inside of this y1, y2 plane. And I take this k constant, so I'm measuring the point. I'm taking a point where the slopes are always equals to the constant k. Okay? So when this happens, then these points whose slopes are this constant k is given by this equals to k. So if I rewrite this equation, then it becomes y2 equals to these equations. So let me give a picture of this graph. So I already did the MATLAB code here, and then there's a small variation of the iteration and the conditional loop. So let me explain what that is. So we have a van der Pol equation, and the curve of this curve. So it's not the curve. So curve consisting of the point where the solution curve passing through that point having the same slope is called the isosceles. Okay. So this isosceles is given by y2 equals to y1 over this factor here, and I set this mu equals to 0.1, for example, and I want to draw this curve into y1, y2 plane. So by varying this k constant. So in the textbook, they uses the k as -5, -1, and so on here. So I use the same examples of k. And when I use the for loop, I can set k to be equals to this array. So because of the working process of a for loop, when I took this, it doesn't mean that I'm taking k as an array variable. It simply means that I'm taking k from each entry of this array, because I use this equation in the for loop. So whenever it iterates this for loop, k variable changes from -5, -1, -1 over 2, and so on. So first of all, when this for loop works first, at the first time, and k is -5. So I set the cases where k is less than or equal to mu or bigger than mu, because when I don't have this if loop, then you see this part, the denominator of this y2 could be 0. If the denominator becomes 0, it diverges. But actually, the isosceles does not diverge. It only because we cannot take the interval of y1 where y2 diverges. It simply doesn't exist. It's like asymptotic line, vertical asymptotic line. I don't want to draw the vertical asymptotic line. So I set these two cases where there is a vertical asymptotic line or there's no vertical asymptotic lines. So I draw this y2 graph first by setting this y2 array using given y1 range, and then plot y1 and y2 and hold on, and it iterates 6 times. And I'll also draw this solution curve together with isosceles here. And I draw 2 solution curves. One is starting from initial value 1, 1, where y1 is 1 and y2 is 1. And the other is when y1 is 3 and y2 is 3. So going back to the original interpretation, y1 is y or y2 is y prime. So basically I'm solving this van der Pol equation with the initial condition y0 is 1 and y prime 0 is 1. And in this case is y0 is 3 and y prime 0 is 3. So I also plot these 2 graphs. I didn't put the hold on here because I already put the hold on in the front plot, in the previous plots. So, and then after I draw all the plots, I finish off by drawing the plots together, so hold off, and then I set my axis. I set my figure axis to be -5 to -5, -5 to 5, and same for the y-axis. So when I draw this, this is the graph. So first of all, there is a diverging curve from 0.0. Again, 0, 0 is the stable point. If y1 and y2 are both 0, it's a stable solution. Okay, so this is stable solution, but I mean it's equilibrium solution. Okay, and then it diverges from 0, 0. But these lines are not solution curves. These lines are isosceles, meaning that if the solution curve passes through one point in this curve, then another solution curve passing through another point in the same curve will have the same slope. So it's the collection of points where the solution curve has the same slope. And this isosceles kind of gives you idea how the solution curve will look like, because basically it will circle around, but your circle is not a perfect circle because there is a small variation on this isosceles. If the isosceles are exactly the rays emanating from 0, 0 with a straight line, then it will be a straight perfect circle. Every solution curve will be perfect circle, but it's not a perfect circle here. And then let's look at actual solution curve. The red one is the solution curve passing through 1, 1 initial point, and blue one is starting from 3, 3. Okay, the red one actually converging to the larger circle, and blue one converging to the smaller circle, and you can imagine that there is a middle circle which is stable, which means that it always circles around the same closed loop. So when there is the physical interpretation is when there is small amount of energy in the beginning, then it will converge to a larger energy state. And if you have a large energy state, if you start from the large energy state, then it will emanate energies and then converge to small energy state. So it's like converging to the stable point, but basically this solution, the middle solution here, the infinite loop, looks like an infinite loop, is not a station solution. So let me explain that in the simplest example. So when you solve, so this is a van der Pol equation, and plus what? What was the last one? Y. So when you solve van der Pol equation, so let me make a very simplest example. Compare that with y double prime plus y equals 0. Okay, suppose that there's nothing here, assuming that mu is 0. So let's try to make this equation into system of first order linear equations. So first, by setting y1 equals y and y2 equals y prime, then the system becomes y1 prime, y2 prime is equals to y2, and y2 prime is minus y, so it's minus y1. And you can write this as a matrix representation as 0, 1, minus 1, 0. y1, y2. So this simplest second order differential equation is the system of differential equation when in terms of y1 and y2 with this matrix A, 0, 1, minus 1, 0. And we categorize all the nodes in the system of first order differential equations. And in this case, we have zeros on diagonal, and on off diagonal we have opposite sign. So 0, 0 is the stable solution. Stable constant solution is the center node. Okay. So basically, if you draw your solution in y1, y2 prime, y2 plane, here's the central node, and all the solution will circle around this node. So depending on the initial value, it will change the radius, but basic behavior is the same. Now, in this case, it's almost similar, so except that you have a negative minus, a negative mu times some weird constant here. So basically, what we are talking about is, let me rewrite this into y1 prime equals to y2, and y2 prime equals to mu 1 minus y1 square and y2 minus y1, right? So y1 and y2 prime is equals to here y2 mu 1 minus y1 square, y2 minus y1. So you cannot simply write as a linear terms here, but you can linearize these terms. If you linearize these ones, then this is almost equals to y2. How about linearize these terms? So minus y1 is already linearized, so it's minus y1. So how about 1 minus y1 square y2? So if you linearize this, 1 minus y1 square y2 is y2 minus y1 square y2. So it's a polynomial. When you linearize your polynomial, it's simply you chop up all the higher order terms away, and then the first order term survives. So this linearized to y2. Okay? So this is mu y2, and this now becomes 0, 1, and here minus 1 mu y1, y2. Okay. So let's compare the simplest case. This is the van der Pol case when mu is actually 0, and we know that this is this has a central node. And look at a little bit more general case. It's not entirely general because we linearize this differential equation. But you see the difference between this one and this one is that the right lower corner entry are mu or 0. If mu is almost 0, almost close to 0, then it becomes similar to this equation, and this differential equation has central node, so it has a perfect cycle. The perfect cycle means that there is an oscillation, infinite oscillation. So you see, when mu is small, we can imagine that there is an infinite oscillation in van der Pol equation. So without actually looking at the numerical solution or finding an exact solution of the van der Pol equation by linear approximation, we know that this solution curve will kind of look like an infinite oscillation. So, any questions? Is it okay to did you understand the linear approximation part? It's very important to interpret the differential equation without solving exact solutions or numerical solution. Let me show you another code here. So the first example was when mu is 0.1, comparatively close to 0. And what happens when mu is large? Let's say mu is 1, then I did my homework here, so it looks like this. So we have, so first of all, this curve is a asymptotic line. It's drawn, it should not be here. It's because of the limitation of the MATLAB. So MATLAB tries to connect, the plot command always try to connect all the dots here. So basically the here consists of these lines and these lines. There's no asymptotic line, vertical asymptotic line here. And red and other lines are isosceles. Okay, all the points have the same slope. And actual solution curve looks like this. It's circle now because mu is not equal to 0. So if mu is away from 0 and more, then the stable curve will deviate from the shape of the circle. So when initial value is small, comparatively small, 0.5, 0.5, then it will gain an energy and then converge to this solution curve. And if start from the large energy, let's say minus 2,2, then it will emanate energy and converge to small energy. So this shape, it's not a circle, but it's a closed loop, it's kind of oscillating state, right? It's oscillating, but it's not oscillating like a sine and cosine curve. It's some weird figure. So again, what I mean by oscillation is that it's oscillating in time, not oscillating inside of this y1, y2 plane. So what I'm trying to say is this y1 and y2 are actually oscillating function, and the result is the following. So we have give me a little bit more time here. So we have this figure is the result of plot of y1 and y2. I want to draw this y1 and y2 in terms of t. Okay, it takes a little bit more time to. Okay, so I forgot this one. Okay, all right. So when I draw this y1 and y2 in terms of time, it oscillates, but it's not a sinusoidal curve. It's a periodic curve, but it's not a sine or cosine curve. Okay, so it oscillates like this. So y1 oscillates like red one, and y2 oscillates like ones here. Okay. Any questions? No questions? So this is the equation, the result of the solution when the initial condition is minus 2 and 2. Let's see. What about we have small mu in the previous case. In the small mu, and the initial value is 1, 1 here. So let's see how the graph looks like. So we have, it's still not a sinusoidal curve, but it's closer to sinusoidal curve than the previous. I'm sorry, I forgot to change the mu. Okay, mu is 0.1. Okay, 0.1. Okay. So it's close to the sinusoidal curve, but you see the amplitude is growing, right? It's growing here. And if I set this time to be 0 to 40 instead of 20, then you see it still is not saturating. So at some point it is saturating. So let me change to 60 here. So you see, after 20 minutes of time or 40, the amplitude saturates. So it's like movement inside, movement on the circle. So it becomes a circular movement in this case. It's when mu is very small, it's 0.1. Okay, if mu is not small, then it's not a circular curve. Okay, so let's move on. So double pendulum. So I think maybe that's not the contents covered in the high school, but it's very interesting subject if you done a small research on high school about physics. So when you model the double pendulum, so when you model the single pendulum, it's very simple. It's just a oscillation, right? So, and also we already did that in the previous case, previous examples. And for the double pendulum case, it's not like a double spring. So double spring is modeled by second order differential equation, two second order differential equation. But when you model the double pendulum, you need to apply Euler-Lagrange equation. And Euler-Lagrange equation requires to understand Lagrangian, which is the kinetic energy minus the potential energy. Usually the total energy is the kinetic energy plus the potential energy. Lagrangian is not the sum of two energy, it's the subtraction of two energy. And Euler-Lagrange equation says that, so here's the general setup here. So let's say the kinetic energy is usually denoted by 1/2 mv square. So it's proportional to the square of the velocity, and the potential energy usually depends on the height or the position. So let's say, let's say this way. So and then I'm going to rewrite my velocity and height in terms of a position vector. So let's say our x is a position vector, and x dot, which measures the difference of position vector, is the velocity. And also, I'm going to write my height as a position vector. Okay. So then I can rewrite my Lagrangian as x dot square minus mgx. Okay. So basically, it's a function of x dot and x. So Lagrangian is usually a function of x and x dot. Okay. So x doesn't have to be actual position variable. It's a variable that measures, that determines the position of an object at some time. So when I model my double pendulum, so here's the ceiling, and here's one object, and here's another object. I have fixed lengths of pendulum, two pendulums, and the mass of two objects are fixed. And what changes is the angle of this pendulum line, right? So let's say theta 1 is the angle between the vertical line to this pendulum, and then theta 2 is the angle between vertical line and the second pendulum. So the position of M1 and M2 are exactly determined by theta 1 and theta 2. Okay? So I can consider my theta 1 and theta 2 as if it works as the work of x. Okay? So my L is now function of theta 1, theta 2, and theta 1 dot and theta 2 dot. Okay? So let me explain. I will explain why it requires 4 elements here. So let's first compute the kinetic energy and potential energy. although there is a formula already here, 끊겨요? Okay, so 잠시만요. 지금은 어때요? 지금도 끊겨요? 지금은 어때요? 지금도 끊겨요? 지금 좀 괜찮았어요? 네. 조금 딜레이가 있긴 하거든요, 지금. 지금은 핑이 좋거든요. 지금 어때요? 조금 빨간색 안 됐다네. 지금은 조금 안정된 것 같거든요. 일단은 하다가 또 끊기면은 잠깐 얘기 다시 할게요. Okay, so let me explain the double pendulum again. So Lagrangian is kinetic energy minus the potential energy. Kinetic energy depends on the position and the velocity. So it's a function of x and x dot. And potential energy only depends on the position, so it's a function of x. So the Lagrangian itself is a function of position and velocity, so it's a function of x and x dot. So when you determine your position of your object, sometimes you need two coordinates, x or y, right? So when I say the position x, it might consist of many other variables, so x1, x2, or so on. So in our case, in the double pendulum case, the position vector is determined by theta 1 and theta 2. Theta 1 is the angle between the vertical line and the first pendulum, and theta 2 is the angle between vertical line and the second pendulum. So when you know theta 1 and theta 2, you can fully determine the x and y coordinates of m1 and m2. And here's the formula. Okay? So first of all, it's a very simple formula, but I'm taking this pivot as 0, 0. Okay? So my y1 is negative of this L1 cosine theta 1, and so on. And Euler-Lagrange equation is telling you that the partial derivative of Lagrangian with respect to theta I dot, and also take the derivative in terms of t minus the Lagrangian partial derivative of Lagrangian in terms of theta I equals to 0. And that's for I from 1 to 2. So there are two set of equations to solve simultaneously. And again, I'm emphasizing that the first partial derivative is the derivative in terms of theta I dot, not theta I. Okay, so you have to consider your theta I and theta I dot as a separate variable. So let's compute the equation here. So kinetic energy is 1 over 2 m1. So first, kinetic energy of m1 is the 1 over 2 m1 times the velocity. And this velocity is a velocity on two-dimensional plane. So it's the velocity of a vector v, which is coordinate x1 dot and y1 dot. Okay. So when you take v, the size of v and square, that is the x1 dot square plus y1 dot square. So that's why we have this term. Okay. And again, when you plug in the formula x1 and y1, these formula into this equation, you can make cosine square plus sine square equals 1, so it becomes simply 1 over 2 m1 L1 square theta 1 dot square. Okay. So T2 is similar, so you have this as a kinetic energy, and apply T2 x2 y2 term inside of this formula, you get these expressions. So let me rewrite that in the blackboard so that you can formulate yourself. So T2 is 1 over 2 m2 x2 dot y2 dot 1 over 2 m2. So here we have x2 equals to L1 sine theta 1 plus L2 sine theta 2, and y2 equals minus L1 cosine theta 1 minus L2 cosine theta 2. So when you take a dot here, you're taking a derivative in terms of t. So x2 dot, which is dx2 dt, is L1 cosine theta 1 dot, okay, and L2 cosine theta 2 dot, okay, and y2 dot is minus L1 plus L1 sine theta 1 dot, and L2 sine theta 2 dot. So I'm going to plug this into the formula. So this is L1 cosine theta 1 dot, L2 cosine theta 2 dot square, and L1 sine theta 1 dot plus L2 sine theta 2 dot. Right? So let's combine two terms here. So we have a cosine square and sine square when I take the square here, and also cosine square, sine square. So it's 1 over 2 m2 of L1 square theta 1 dot square and L2 square theta 2 dot square. And how about the middle? We have 2 times of L1, L2, theta 1 dot, theta 2 dot. It's common in this product and this product. And here we have cosine theta 1, cosine theta 2. And here we have plus sine theta 1, sine theta 2. So this guy becomes 1 over 2 m2 L1 square and theta 1 square 1 over 2. Let's combine these two. So plus L2 square theta 2 dot square and plus combine these two terms, we have m2 L1 L2 theta 1 dot square theta 2 dot square, and this is cosine theta 1 minus theta 2. Okay, so that's the kinetic energy on the second object m2. Consider 또 끊겨요? 어디서부터 끊겼어요? 어디서부터 끊겼어요? 다시 설명해 줄까요? 아, 진짜? Okay, so we are going to, so these equations are a result of Euler-Lagrange equation. It's very long computation, so I'm not going to do all the computation, but as an example, let me do the partial derivative of t2. Okay, so I will show you how to take a partial derivative of t2. So let's take a partial derivative of t2 in the theta 1 dot. Okay, so here we are going to consider theta 1, theta 2, and theta 2 dot as a constant, and assume that there are only theta 1 dot as a variable. So okay, so this is the t2. So first term has theta 1 dot. So this is m2 L1 square theta 1 dot. Okay, and here there's no theta 1 dot term, so nothing happens. And for this one, we have m2 L1 L2 and theta 2 dot, because theta 1 dot, this is a why there is a square? There's no square. Okay, theta 1 is there's order 1 theta 1, theta 2, and cosine theta 1 minus theta 2. So that's partial derivative. 오늘 핑이 안 좋네요. 조금 끊겼죠? 괜찮았어요? 랜선으로 다음 시간에는 제가 랜선으로 해볼게요. 지금 이게 학교 인터넷 저기 뭐야 무슨 인터넷이 좀 느리면은 그런 것 같아요. 왔다 갔다 하는 것 같은데 또 끊긴다. So okay, so this is how you take a partial derivative. So when you take the Lagrangian partial derivative theta 1 dot, that means you're taking t1 plus t2 minus v1 minus v2 partial derivative of theta 1 dot. So basically you take partial derivative of t1 by theta 1 dot, partial derivative, and partial derivative. And we only did this part, okay? What we have shown here is this part. You have to do the other parts. So, and then, this is not it. You have to take a derivative of this whole thing again, the dt of del L del theta 1 dot. So that's derivative of each terms here, del t1, del theta 1 dot, dt2, del theta 1 dot, and so on. So we have to take a derivative in terms of t of these terms. And then that's get more complicated because when I take a derivative of t, I have to take theta 1, theta 2, and theta 1 dot, theta 2 dot as a function of t. So you cannot ignore these as a constants. So one more computation is ddt of del t2 del theta 1 dot is m2 L1 square, and derivative of theta 1 dot, which is becomes theta 1 double dot, okay? And then here we have m2 L1 L2 of what? First, you take the derivative of theta 2 dot, theta 2 double dot, cosine theta 1 minus theta 2, and then take a derivative of cosine part. It becomes minus theta 2 dot of sine theta 1 minus theta 2 times theta 1 dot minus theta 2 dot. This alone is very long summation. We need 3 more terms to compute this, and that's not over. We have to take dl d theta 1. So you have to do the 4 more computation, okay? And then combine this to make one big formula of first Euler-Lagrange equation, this equation, and you have to do this whole thing again with the second one. And then becomes a full system of differential equation, okay? So it's very long and tedious. If you make a mistake once, everything collapses. So I'm not going to do this. And let's look at the result. Here's the result. So this has a second order derivative here, and also the coefficient is not always constant. It contains sometimes the function itself, and there's a sine and cosine is applied to the functions. So this is not a linear function. Okay, so this is not the differential equation that we can solve easily. However, I will show you how to do this by hand. Before that, let's try to linearize this differential equation. Okay. In the beginning of previous lecture, we mentioned briefly about the linear approximation and Taylor series, and this is a definition of Taylor series. Basically, you have a function which is infinitely differentiable. Then there is a series, which means that it's an infinite sum of numbers, such that it contains the variable x and x minus c to the nth power terms, and coefficient are the nth order derivative at some point c divided by n factorial. So this is called the Taylor series at c. Okay, so this Taylor series approximates the value of function near c. So usually we take c as a 0. So we're going to approximate the value of function near 0. the result is when you take function sine, then the Taylor series looks like this, and cosine, then Taylor series looks like this. And we know that this x is close to 0, which means that it's very small value. So x cubed, x fifths, x squared, x fourth are very small compared to the first order terms, first terms here. So we can guess that sine x is almost equals to x and cosine x is almost equals to 1. Okay? When x is very close to 0. So when we take a linear approximation of Lagrangian in the first place, then the Lagrangian becomes very simple. This equation. Okay? If you apply the Euler-Lagrange equation to this Lagrangian, so this is not actual Lagrangian, it's an approximation of Lagrangian, because assuming that this zeta 1 and zeta 2 are very small, okay, then Euler-Lagrangian gives us comparatively simpler form of differential equation. So you don't have a cosine or sine. It's just the linear terms here. Okay? Everything is linear. So let's take second order terms here. So this is second order, second order, second order, second order. And leave all the other first order, that's zero order, sorry, to the right hand side. So let me express these terms in other format. So although I put that in the matrix format, let me rewrite that in the blackboard. So the second order term so it has M1, M2, L2 here. Let's say make up. So let me rewrite this one again. So here we have zeta 1 double dot and M2 L2 L1, sorry, L1 and zeta 2 double dot, and then minus of M1 M2 of G L1 zeta 1. Okay, so and then second equation is M2 L1 L2 zeta 1 double dot and M2 L2 square zeta 2 double dot equals to minus M2G L2 zeta 2. So I'm going to cancel something. So we have L2 L1, sorry, so M2 L2, M2 L2, M2 L2 everywhere in the second equation. So let's delete this. M2 L2, and on the first equation, this one is, sorry, L1. So this is L1. So there are L1 everywhere. Okay, so I'm going to delete L1, L1 and L1. So I'm going to write this system of equation in terms of matrix representation. So we have M1, M2, L1 applying to zeta 1 double prime, okay? And then M2, L2 has zeta 2 double prime. So when you compute the first row of matrix multiplication, you get the first left hand side of the first equation. And that equals to, so on the right hand side, we get minus M1, M2, G, zeta 1. Zeta 1, okay? And 0, zeta 2. How about the second equation? We have L1 and L2, zeta 2 double dot, and we have minus G. So minus G on the second component, minus G, 0. So that's the equation. So we can take the inverse matrix of this 2 by 2 matrix. So zeta 1 double dot, zeta 2 double dot equals to M1, M2, L1, M2, L2, L1, and L2 inverse times minus M1, M2, G, 0, 0, minus G times zeta 1 and zeta 2. Okay? So this is our second, the differential equation. So this is the differential equation. And when you take when you take inverse matrix exists if and only if the determinant is not 0. What's the determinant of this matrix? So M1, M2, L1, L2 minus M2, L1, L2. So this equals to, so there's a canceling of M2 in this guy. So this is M1, L1, and L2. So if this determinant is 0, it means that the mass of first object is 0, or the lengths of two pendulum, one of the lengths of two pendulums are 0. It does not make sense, right? So cannot be 0. So always inverse matrix works. So we have this differential equation, and once you know this type of differential equation, you can solve exactly the solution of system using the Laplacian, Laplace operator, Laplace transform. We're not going to talk about this yet. However, we can solve the numerical solution of differential equation. Let me explain that here. So when you solve a numerical solution, you always have to convert that into system of first order differential equations. These are system of second order differential equation. So I'm going to change each second order differential equation into system of two first order differential equation. So let's say y1 is equals to zeta 1, and y2 is zeta 2, and y3 is zeta 1 dot, and y4 is zeta 2 dot. So then y1 prime, y2 prime, y3 prime, y4 prime is equals to, this guy is zeta 1 prime, but zeta 1 prime is y3, and y2 prime is zeta 2 prime, but that's zeta y4. So I'm not going to write anything about the derivative on the right hand side. Okay? So I'm trying to write in terms of y1 to y4. How about y3 prime? So y3 prime is zeta 1 double dot. Zeta 1 double dot is given by this term. So let's not write right now. I'm going to rewrite this in terms of y1, y2, y3, y4, multiplying to some big 4 by 4 matrix. This is 4 by 4 matrix. Okay. So what happens here? for the first two terms here, I need y3 for the first, so this 0, 0, 1, 0. Okay. How about y4? This is 0, 0, 0, 1. And for the rest of the terms, this y1 double prime or y3 prime only depends on this y1 and y2, right? So there's nothing on here. So what comes here on the left corner, left bottom corner here is that the result of these matrix. Okay, so these matrix goes to this place. Okay. So, well, you can compute the inverse matrix of 2 by 2 matrix. So you can multiply these two 2 by 2 matrix again. So suppose that you already done that. Let me show you the MATLAB code of finding this numerical solution. Before we move to the MATLAB screen, any questions? Any questions on here? So again, this is y3 prime and y4 prime, okay? And this part is y1 and y2. So I'm putting this part into the big equation here. So let's see. Okay. Okay. So here's double pendulum case. So this one is the actual equation of double pendulum without linear approximation. So let me show you result of linear approximation first. So in the linear approximation, so first of all, so I forgot. Oh, so there's a mistake here. So it's 0, 0, 1, 0 and 0, 0, 0, 1. Oh, okay. So yeah, in this case, I changed my order of the variables here. So let me change this to L1, L2, 0. So I already computed the inverse matrix, and I plug in these parts. Okay, so so this is the big matrix, 4 by 4 matrix that I put in the blackboard. Okay, 0, 0, 1, 0, and some 2 by 2 matrix, and then 0, 0. So and then here I have to actually okay, so what comes on this part what comes on this part of my calculation is so in the blackboard I did my computation this part already, and I inserted this part to here, and then I changed this to result of this minus m1 m2 gy1 and minus gy2. Okay, so you have to understand that in the code. So that's the result, and then I'm drawing my so I'm drawing the y1 and y2, so which means the theta 1 and theta 2. Okay, so let's see the okay, so t1. Okay, so this is a initial condition. Okay. So my initial condition of the theta 1 is 1, okay, and theta 2 is minus 1, and theta 1 prime is 0.5, and theta 2 is minus 0.5. So let me delete this. Again. So this is the result. So the blue one, blue one is the first pendulum, M1, the movement of mass 1, and the red one is the movement of M2. Okay, because I guess I'm tracking that with the initial condition here. The blue one starts from 1 and red one starts from 1. And then it's a perfect oscillation. It's oscillating from minus 1.5 or to 1.5. And this only measures the oscillation of the angle. When you try to put a plot on XY plane of actual movement of object M1 and M2, you have to use animation or other method. For example, I hope it's not lagging. So let me show you the animation on the MATLAB. So this will show you the actual movement without linear movement. 다시 설명해 드릴 테니까 이 매트랩은 조금 끊기는 것 같더라고요. 껐는데. Okay, so here is for, okay, and then so y1, y2, the column, first column and second column is theta 1. So let's see, x1 is what? L1 times sine theta 1, right? And x2 is L1 plus L1 sine y1 plus L2 sine y2, and y1 is L1 cosine y1 and y2 is L1 cosine y minus, sorry, so minus and minus L2 cosine y2. Okay, so I set my x1 and y2, x and y, and then let's try to plot this. So when I from 1 to length of t, I'm going to plot two things here. So plot first x1i and y1i as a dot, a red dot with marker size 20, and hold on, and plot x2i, y2i, and blue dot as marker size 20, and hold off and draw now, and okay. Okay, so I'm drawing a movement of a point by changing the time, the time entries here. Let's see, 24 sine, forgot the parentheses, so here sine, okay. Wait, fix my bus. So let's see, axis is from L1, L2, L1, 2. So let's see, minus 4 to 4 of minus 4, 0. Okay. Axis equal. Okay. Axis equal minus 4, 4. Minus 잠깐만요. 뭔가 좀 아까 켜놨던 게 계속 나오는 것 같은데. 아이고 씨. 자꾸 켜놨던 게 나와가지고. 중지. 중지. 백 가지만 할게요. 같이 그 방송이랑 켜놓으니까 느린 것 같은데. 대충 x, y, sin sine, cosine. Sine y2, x2, y2. 그리고 문중이 조금 이상한데 좀 중지가 안 돼가지고 그렇거든요. 다시 그리긴 해야 되는데, 오케이, so 봅시다. 그냥 여기서 이제 마무리하면서 끝낼게요. So red one is the M1, the M pendulum, and blue one is M2 pendulum. So it's blue one is hanging on the red one, and red one is hanging on the top of the roof. So movement is a little bit weird. The reason why it's weird is because the axis is moving. So if I fix my axis, then it will move like a pendulum. But so anyway, so I didn't put the line in between here, so you can make it more nice figure, putting the line in between these two lines, and then a line from the red one to the ceiling. And this one is an approximation by linear approximation. But if you use the actual pendulum differential equation, then it will move different from this one. So it only works when your theta 1 and theta 2 are very small, close to 0. In this example, I use my theta to be not that small, okay? So I use my radian 1, radian minus 1. So radian 1 is almost 60 degrees, right? So it's very large distance, okay? So it's a large movement. So it does not represent actual movement here. 끝났나? 참. So when you if you want to use actual Lagrange, then equation, okay, one. So in this equation, I did not use the matrix multiplication. I used the matrix multiplication, but this term is a little bit more complicated. Okay, so this term gets a little bit more complicated. So instead of simply y3 and y4, this term becomes, so I have to change this to y1, y2, y3, or 4. Let me change right now. So this one is 1 and 0, 0 here, and 0, 0. And here we have 0, 0. And this is 3, 4. Is this yes? So this goes to the end. Here we have 3, 4. Okay. So and then y1, y2. Okay. So this is actual movement. 끝났구나. Okay. So let's look at this one again. 아, 이게 자꾸 움직이냐 이게. 아우. 아까보다는 조금 낫는데 좀 아니죠 이것도. 엑시스 이꼴을 빼야겠다. 아니, 아이고 참 이것도 아니네. 다시 그릴게요. 오케이. 이게 좀 나았죠. 좀 보시면 천장 0,0에 달려 있는데 지금 여기 움직이는 거예요. 그러니까 조금 더 그림을 예쁘게 만들어 볼까요? 여기에다가 플롯 x1 i 그러니까 0,0에서 0x1 i까지 하고 0 y1 i까지 하고 다음에 플롯 x1 i에서 x2 i까지 하고 y1 i에서 y2 i까지 하고 다시 한번 그려봅시다. 그러니까 요런 느낌이에요. 지금 많이 돌아가죠. 지금 거의 막 90도 올라가려고 하는데. 자, 근데 자, 요거랑 그 다음에 실제 모양이랑 비교를 해보자고요. 지금 아까 우리가 비교하려고 했던 건 있는데 같이 봅시다. 여기서 그러니까 요게 원래 양지안으로 한 거고 요 밑에 게 이제 그 다음 그 approximation으로 한 거예요. 그러니까 여기서 이제 일단 잠깐만 요건 일단 지울게요. 이거는 똑같으니까. 자, 그 다음에 이제 지금 subplot 121 여기 한번 봅시다. 122 여기 봅시다. subplot은 뭐냐면 이제 플롯 두 개를 동시에 한 피규어에다 그리는 거예요. 그러니까 겹치 그리는 게 아니고 그러니까 창을 두 개를 그러니까 창은 하나인데 이제 그 두 개의 격자를 동시에 그리는 거예요. 그러니까 왼쪽 오른쪽에. 그러니까 subplot 1, 2 하면요. 1행 2열로 나눠 가지고 그 다음에 나오는 이 플롯 명령어들은 전부 다 그 첫 번째 그려라. 일단 1, 2, 1이란 말은 1, 그 행이 한 개, 열이 두 개인 그래프를 한 창에 그리는데 첫 번째 칸에다가 이 다음부터 나오는 건 그려라. 그 다음에 서플롯 1, 2, 2 했잖아요. 그러면 두 번째 칸에다가 그 다음에 나오는 걸 다 그려라. 그런 뜻이에요. 요거 한번 보자고요. 이렇게 해서 이렇게 하고 결과를 동시에 한번 봅시다. 지금은 T1, T2의 초기 값이 큰 거예요. 크면은 아까 안 맞다고 했죠. linear approximation 작아야 맞아요. 지금 linear approximation을 0에 근처에서 했잖아요. 지금 왼쪽이 실제 움직임이고요. 좀 뭔가 불균일하죠. 그러니까 이게 실제 움직임이에요. 라그랑지안으로. 그러니까 실제 더블 펜들럼은 왼쪽 그림처럼 움직여요. 그러니까 여기서 이제 빨간색, 파란색 세타 값이에요. 그러니까 우리가 실제 펜들럼 하는 건 아까 매틀랩 아까 한 것처럼 다시 봐야 되는데 어쨌든 두 그래프가 다르잖아요. 많이 다르죠. 오른쪽은 되게 균일하고 왼쪽은 아니죠. 근데 왼쪽에 맞는 거예요. 만약에 여기서 이제 초기 값을 좀 작게 봅시다. 0.0 느려. 여기도 0.01 얘는 0.005 굉장히 작게 움직인 거죠. 0.005 이런 식으로 한번 해봅시다. 똑같죠? 왼쪽 오른쪽 똑같죠? 그러니까 똑같은 걸 그린 게 아니고 이쪽은 실제 라그랑지안을 한 거고 오른쪽은 approximation 해서 그린 거예요. 똑같이 나오잖아요. 그러니까 이게 굉장히 폭이 작으면 진폭이 작으면 그러니까 진동각이 작으면 linear approximation을 하는 게 속도가 빠르고 이제 크게 오차가 없는데 진폭이 크면은 linear approximation을 하면 안 돼요. 그러면 일단은 아까 우리가 봤던 것처럼 요거 linear approximation 안 하고 어떻게 되는지 한번 봅시다. 그래서 여기에서 이 상황인데 지금 초기 값은 그대로 갖고 오고요. 그러니까 방금 애니메이션으로 봤던 거는 이제 approximation 했기 때문에 정확한 움직임이 아닌 거예요. 그래서 이걸 똑같이 가져오면 되죠. 이렇게. 뭐야? 큰일 났다. 1000으로 해가지고 100으로 했어야 좀 빨리 되는데. 중지. 이건 빨리 끝났네요. 그리고 아까 잘못된 거 없나? 조금 이상했는데 그림이. 뭐 이렇게. 네, 이게 이제 실제 라그랑지안으로 만든 거예요. 그러니까 실제 더블 펜들럼이 이렇게 움직인다고요. 그러니까 막 좀 이상하게 움직이는 것 같지만은 이게 맞아요. 이게 실제 움직임이에요. 짧게 한번 해볼까요? 점 1, 점 마이너스 점 1, 점 05, 점 05. 양식이긴 하는데, 그러니까 이런 상태에서는 우리가 리니어 어프로크시메이션을 하는 게 큰 이제 오차가 없기 때문에 오히려 계산도 빨라지고 좋은데, 아까처럼 진폭이 큰 경우에는 그렇게 하면 안 된다는 거죠. 자, 일단 이 코드는 제가 매틀랩에 다 LMS에 다 올릴 거예요. 이제 요런 것들 플롯 얘기는 다 했었고, 아까 그 애니메이션 할 때 draw now 하는 거 얘기도 했었죠. 혹시 질문 있으세요? 일단 오늘은 여기까지가 마지막. 맞다, 하나 남았는데 그거는 다음에 합시다. 오늘 여기까지 마지막으로 하고, 혹시 질문 있으세요? 없어요? 중간고사 보험이 7주차까지요. 일단 오늘 한 내용 중에 질문 없어요? Okay, so let's call it here. So thanks for listening, and see you on. So next week we don't have class. Next week is official midterm week, and on the week after next week, on 11th week, we are going to have a midterm on the class. So in class hour, so 1 hour and a half each. 그리고 지금 나가시기 전에 항상 공지를 하자면 엑스트라 홈워크에 오류가 있어가지고 제가 그 첨부 파일을 다시 업데이트 했거든요. 그거 다시 보시고, 빨간색으로 된 부분이 고친 부분이니까 그거 다시 보고 숙제하실 분들은 하시고요. And if you don't take midterm, which means that if you don't submit anything on the LMS on the midterm period, then you will fail the course. It's not count as 0 score. You will get an F. Okay, so even if you don't know how to solve questions on every questions, you have to submit something. You have to submit an blank page so that I know that you attended the midterm. So let me explain it in Korean. 원래 공식적으로 중간고사는 여러분들이 응시를 안 하면은 F가 나가요. 다음 주는 강의 없어요. 만약에 우리가 온라인으로 midterm 치는데 그 뭐 문제를 잘 못 풀겠어가지고 아무것도 제출을 안 한다. 그러면은 F예요. 시험을 안 친 게 되기 때문에. 그러니까 뭐 몰라도 그냥 백지를 내야 돼요. 그래야 제가 0점으로 카운트를 하지, 그걸 안 내면은 안 친 걸로 하기 때문에 꼭 제출하셔야 돼요. 그냥 백지라도 제출을 하셔야 돼요. 그러니까 우리가 지금 정확히 말하면 2주 동안 가진 강의가 없어요. 다음 주는 시험 기간이라서 없고 그 다음 주는 시험을 봐서 없는 거예요. 그리고 중간고사에 매틀랩 나올 거고요. 그러니까 7주차까지니까 매틀랩 지금 하는 매틀랩은 아니에요. 7주차까지 했던 매틀랩 내용을 위주로 나올 거고요. 7주차까지 했던 숙제 범위예요. 그게 정확하게. 그 다음에 시험은 총 6문제인데 월요일에 3문제, 목요일에 3문제, 한 문제당 30분씩 30분 이내에 제출을 하셔야 돼요. 제가 퀴즈는 조금 더 연장을 해드려서 제출할 수 있게 해주는데 시험은 그렇게 연장 안 해드릴 거예요. 30분 안에 제출 완료가 돼야 돼요. 만약 제출이 안 되면은 점수 기록이 안 되는 거예요. 자, 일단은 수업은 끝났고요. 고생하셨고, 난이도, 뭐, 난이도를 어떻게 비교를 해야 되잖아요. 뭐에 비해서? 30분 안에는 당연히 풀 수 있는데, 아니, 매틀랩 스크립트를 뭐 짜야 풀 수 있는 거죠. 네, 기본적으로는. 근데, 매틀랩 같은 경우에는 제가 이제 코드를 여러분들이 직접 했다는 거를 뭐 사진을 찍어서 이제 제출을 하라고 할 거예요. 과제랑 비교하면은 과제에 비해서는 좀 더 분명하게 무엇을 해라라고 명시는 할 거예요. 근데 이제 난이도는 과제보다는 좀 더 클 수 있죠. 과제는 좀 더 자유롭게 적을 수 있었던 반면에 시험은 제가 분명하게 어떤 답을 요구하는지를 명시를 할 거예요. 그리고 아까 처음에 이제 몇 명 없을 때 얘기했는데 그 우수 강의로 여러분들이 선정을 많이 해줘가지고 고맙게도 제가 인터뷰 한다고 하거든요. 그래서 셀프 인터뷰를 할 건데 혹시 여러분들 질문지는 있는데 여러분들 궁금한 거 있으면 지금 알려주세요. 그러면은 인터뷰할 때 그 얘기도 좀 할게요. 퀴즈 난이도가 어땠어요? 그러니까 제가 피드백을 못 받아서 너무 시험이 어려우면 또 안 되니까 퀴즈 난이도가 지금 어때요? 시간 내에 풀 수는 있는 거예요? 조금 딜레이가 퀴즈 난이도는 뭐 할만해요? 네. 그래서 뭐 다행이고 근데 여하튼 원래 이제 오프라인으로 퀴즈 보거나 시험 보면은 이렇게 보치고 좀 실수하는 것도 좀 덜하고 하는데 온라인으로 하다 보니까 좀 빡빡하잖아요. 시간이 모자란 것 같고. 그래서 그런 부분은 최대한 감점이 안 되게 얘기는 할 건데, 퀴즈보다는 조금 더 서술은 하셔야 될 거예요. 그러니까 퀴즈는 완벽하게 이제 계산 위주로만 제가 냈었고, 이제 시험 같은 경우에는 조금 서술이 들어가기 때문에, 그거는 양을 여러분들이 맞추셔야 돼요. 서술을 막 여러 말을 많이 하면은 당연히 시간이 모자랄 거고 핵심, 제가 원하는 핵심이 있잖아요. 수업 시간에 강조하고 얘기했던 그 핵심을 이제 적으면은 시간이 충분할 거고. 그러니까 어떤 사람한테는 되게 시간이 적을 수도 있고, 어떤 사람한테는 시간이 충분할 수도 있는데, 이제 그거는 문제 때문에 그런 게 아니고, 그러니까 여러분들이 제가 원하는 그 질문의 핵심을 알고 있으면은 쉽고, 아니면은 어려운 거예요. 계산도 사실은 마찬가지지만은, 그렇게 복잡한 계산은 저는 안 내요. 뭐 혹시 인터뷰 할 때 대답해 줬으면 하는 질문들 있어요? 네, 없으면은 오늘 여기까지 하고 네. 일단 그러니까 다음 주에 시험 보는 분 많이 없잖아요. 그래서 다음 주 어떻게 하시겠어요? 다음 주에 좀 실시간으로 질문을 받는 시간을 가질까요? 아니면 그냥 쉬실래요? 그러니까 유튜브로 안 하고 그 저희 LMS에 있는 걸로 그 화상 채팅처럼 실시간으로 좀 질문 받는 거, 그 시간을 좀 가질까요? 아니면 뭐 사람들이 많지 않아가지고 지금 12명 들어와 있는데 12명 의견이 전부인 건 아니니까 별로? 그러면 그냥 다음 주는 그냥 아예 없는 걸로 그렇게 할까요? 따로 뭐 오피스 아워처럼 이렇게 질문 받는 시간 없고, 예, 공부하는 걸로, 네, 각자 공부하는 걸로. 질문 있으면 이메일로 주시고, 네, 오늘 고생하셨습니다. 이제 거의 끝났어요, 학기도. 중간고사 기간 잘 보내시고요. 다 다음 주에 봅시다.